Hello and welcome to AP Calculus. My name is Daniel Choi and I'm going to be starting the series where I teach you guys calculus. So our first lesson in calculus or AP Calculus is about limits because they're really important to set a foundation for us to dive deeper into AP Calculus. So what are limits? Limits are defined as the value that a function approaches as the input approaches some value. Some of the introductory ways that you can solve or find a limit are graphically, numerically, and algebraically. Today we're going to cover graphically and numerically, and then we will cover solving limits algebraically in our next lesson. So the following is the method with which limit statements are written. So first you start by writing the limit. So you write lim. Then you write the function right next to it. So f of x, whatever they give you, or whatever the function is decided to be. And then finally you write underneath limit, you say that x approaches c, with c being whatever value that your means has to find the limit at. So an extension into limits is actually left and right hand limits. So these are important in that they show whether a limit actually exists at value c. They're written as the same as the limit form shown in the last slide. However, like this. However, so you can notice right here, an important difference is that for the right-hand limit, there's a positive exponent, and then for the left-hand limit, there's a negative exponent. And you can see that in the pictures. In order for a limit to exist at value c, the right-handed limit and the left-handed limit have to equal each other. Otherwise, the limit, like if this equals infinity and the left-hand limit equals negative infinity, then this limit is deemed as does not exist, or DNA, which we would write as our answer. Additionally, you can also determine if a function is continuous at point C, meaning that there are no jumps, there are no discontinuities or any holes, if f of c is equivalent to the limit as x approaches value c, as a function approaches value c. So we're going to start off with our limits numerically example. So first off, I'm going to be drawing on this and going along with you guys. All right, so first off, we only have one example, but it's a longer example, so that's why we only have one. Okay, so first off, we want to simplify the function that we're given. So we want to factor the top, 2x minus 1, and then the other one is x plus 3. On the bottom is x plus 3, and then x minus 3. So we can cross these out, so our function is equal to, and simplified version of our function is divided by x minus 3. So now what we want to do is we want to fill in each of these tables because they're going to help us find certain limits. And we're just going to plug in 2.75 into this. Yeah, and I'm gonna just use a calculator and just read out what's going on. Actually, okay. I hope you guys can see this. But actually, wait. Okay, I do believe that you guys can see it now. Yeah. Okay, you guys should be able to see it. All right, sorry, I'm just gonna have to rewrite what I wrote here. But if you guys just want, I'll just write down the final result, and if you guys aren't sure, just rewind maybe like 20 seconds, and you'll be able to get it. All right, so so two times 2.75 minus 1 divided by our first. Sorry, 4.5 divided by 2.75 minus. I'll just do 2.75 minus 2.75 minus 3. So it's negative 2.5. So 4.5 divided by negative 0.25. And then we know that the negative's there, so it's just negative 18. So we'll write that down. I'm going to do the rest of these just aloud and not on this calculator because this calculator turns out to be very difficult to use. I guess I'm not used to using a calculator like I use my Inspire typically. All right, so I'm just gonna read out the things. All right, so our next one is 2.9. So 2 times 2.9 minus 1 is equal to 4.8. 2.9 minus 3 is equal to negative 0.1. So 4.8 divided by the quantity, negative 0.1, which equals negative 48. And now we're going to do 2.99. So 2 times 2.99 minus 1 is equal to 4.98. 2.99 minus 3 is equal to negative 0.01. So 4.98 divided by negative 0.01 is equal to negative 498. So you can see that as it gets closer and closer to 3, it's becoming larger and larger. So now we're going to do 2.999. 2.999. So 2 times 2.999 minus 1 is equal to 4.998. 2.999 minus 3 is equal to negative 0.001. So 4.998 divided by negative 0.001 is equal to negative 4,998. So we can see that as it gets very close to 3, it's going negative infinity. Now we're going to try 3.001. So it's only 2 thousandths different from 2.999, so we'll use that. 2 times 3.001 minus 1 is equal to 5.002. 3.001 minus 3 is equal to 0.001. So 5.002 divided by 0.001 is equal to 5,002. So right away, you notice that as it becomes more than 3, it's like very high number, so you would presume infinity. So we're going to try again. 42 times 3.01 minus 1, 5.02 divided by 3.01 minus 3 is equal to 502. So now it's getting smaller again. Times 3.1 minus 1 divided by the quantity, 3.01 minus 3. So that's 500. Oh, what do I do? Oh, it's 3.1. 3.01. So then it becomes 52. Now we got your big jump. So 2 times 3.75 minus 1 divided by the quantity, 3.75 minus 3 is equal to 8.8. Just erase this. 0.66 repeating. Okay, so I'm going to do this again. It takes a lot of time, so I'm just going to do it and I'll just fill it out. I'm not going to recite everything I'm doing. It becomes 1.2592. Negative 3.1 is 1.1803. So you can see that it's getting smaller. Sorry, I'll rewrite that better. .1803. All right, now we get smaller. .1680. And then negative 3.001 is 1.66. Oh, sorry, it's 1.1668. Let me just erase all those. One. Right, so you notice how there's very little drops, and it kind of ends up around 1.16-ish. And then negative 2.99, it comes out to be 1.1665. So you know that negative 3 is some value that's likely somewhere in between these two. So it's probably like 1.667 or 6. All right. And negative 2.99 is 1.1652. And then negative 2.9 is 1.525. 1.1525. Sorry, I keep forgetting that one. And then the last one is 1.1304. Okay, so now we're going really big numbers. So this is, I'm just going to do them again quickly. 0. This is 1.9900. This is 1.9514. This is 1.9056. This is 2.1063. This is 2.0. 0.0515. This is 2.0100. This is 2.0050. So you notice the trend with this one, it increase, or it instantly starts decreasing, and then it reaches a 1.9-ish part, and then it goes back up to 2.1, and then it gets bigger from there. Or actually, no, it goes back down again, right? 2. Right here. 0. So it gets go back to smaller. All right. So now with this information that we've figured out with, we're gonna be done by plugging in the x values into this equation that we figured out. Now we're going to figure out the limits. So right here it says the limit of f of x as x approaches 3 from the right side. So now we want to see where we went around 3. So from the right side it approaches infinity, because as you see that it gets increasingly larger very rapidly. And if you went even smaller, you'd find that it was even higher number. So this would be infinity. Now it asks the limit of the function as x approaches -3 from the right side. So -3 from the right side, we would be looking at this graph, or this table, sorry. So you can see that it gets increasingly bigger, but it approaches like 1.16-ish. 1.16, and that would be repeating because you would imagine that's 1.666666. All right, so limit as the function approaches infinity. So now we want to look. It gets infinitely larger. It approaches 2 because it gets, as you start increasing by a lot, you see that it goes on very little, but it goes down. Yeah, it goes down very little, but it's still staying right above 2. So you would say 2. And then this would be the limit as, oh wait, you're supposed to go up and down. All right, I'm gonna go up and down. This 1b is the limit as the function approaches 3 from the left. So that would be here. So it approaches -infinity, because you see how it gets, every time it jumps a lot and gets a lot smaller in the negative direction. So this would be -infinity. And this, finally, okay, that makes more sense. So then now 1c is asking what the limit as the function approaches 3. So now based on the fact that we found out the right-hand limit and the left-hand limit, we learned in the last slide that in order for the limit to exist at a value c, the left-hand and right-hand limit have to be equal to one another. And -infinity and positive infinity are not equal. Therefore, the limit does not exist, so we write d and e. All right, so now we're on to 2b. So the 2b is asking us the limit as f of x approaches -3 from the left side. So now we look at this, the second table again, and we see that it approaches like 1.66, 1.16 again. 666. So these are the same. However, we do want to approximate it to a fraction if we can, and and 1.166 is very similar to like 7/6, and these are equal to each other. Therefore, the limit does exist, and it's 7/6. So finally, 3b for limits numerically is asking us to find the limit as it approaches -infinity. And we can see that it's getting, it's as from the middle, it goes a little up, little by little, and it approaches 2. But so yeah, therefore, the limit as f of x approaches -infinity is 2. So that's our example for limits numerically. Now we're gonna be looking at limits graphically, which yeah, which I think might be easier, might be a little easier to follow at least. Maybe. So limits graphically. Maybe like 2 pages of examples for this one, because these are less lengthy examples. Okay. So first off, our first example So it's asking us find the limit of f of x as x approaches 1 from the right. So now we want to look at 1, and we want to look at the right, and it approaches 1. The limit f of x as x approaches 1 from the left. So we want to go from the left towards 1, and it gets to negative 1. And it's asking us to find the limit of f of x as x approaches 1. Now we learned that this and this limit as the right and left hand limits have to equal each other in order for the limit at x, a value c, to exist, or 1 in this situation. And we can see that it doesn't. So therefore, the limit does not exist. And finally, this is something I kind of touched upon for continuity. So f of 1, you want to find it. Note this is an open circle, and therefore f of 1 is equal to 0. So it's not continuous, and there's not even a limit. Okay, so the next one. Now the limit is x approaches 1 from the right, and that's 1. 1 from the left, also 1. Therefore, the limit exists, and it is 1. And f of 1, because there's a because there's an open circle, it's undefined. There's no actual value that's given, circled, or filled in to be f of 1. All right. Wait. Okay, this is different. So again, 1 from the right is 1. 1 from the left is 1. Therefore, limit is 1. One. However, this question is a little bit different in that there is a value at f of 1, and it's negative 2. So it's not continuous, but there is a limit. Okay, so now next one. Limit as x approaches 0 from the right, that's 1. 0 from the left, 1. Therefore, the limit is 1, and f of 0 is 1. So it's continuous, and the limit exists. All right, so now limit as x approaches, f of x approaches x from the 2 from the right. So if you see it goes towards 2, it goes, this graph would go infinitely up, therefore it approaches positive infinity. And 2 from the left, so it goes straight down. So this would continue straight down for eternity. So it's negative infinity. These are not equal, so that means that the limit does not exist. And f of 2, there's no defined value. It's undefined. It's definitely important to pick up on the terminology like does not exist or it's undefined, because yeah, they're definitely prevalent later. So limit as f of x approaches negative 2 from the right, goes straight down to negative infinity. Limit as negative 2 x approaches negative 2 from the left, straight down again, negative infinity. Therefore, the limit as x approaches negative 2 is negative infinity. And here is asking us for the f of negative 2. There is a filled-in value, and it's 0. So yeah, those were our first couple of examples. Now we're going to go into our next page. Oops. Now let me clear my drawings, and then we'll go to the next page for more limits graphically. Okay, so there are 5 possibilities. Okay. So here, as f of x approaches infinity, it goes straight on forever, so it's infinity. Limit as f of x approaches negative infinity, that's also infinity. Here, f of x approaches infinity, goes straight down, so it's presumably going to go down forever, or it will go down forever, so it's negative infinity. And then as it approaches negative infinity, it goes straight up, so it's positive infinity. And then as f of x approaches positive infinity, it looks like there's a horizontal asymptote at -2, and you can see that it gets infinite closer, so it's -2. As it approaches negative infinity, there's a horizontal asymptote at y equals 4, so it approaches 4. Oh, wait, these are the same thing, so just ignore these. Okay, and then now we want to look at these examples. So here, as f of x approaches infinity, you see how it oscillates, but it's going every time it keeps going, it's going smaller and smaller and smaller, and it gets closer to 0. And then over here, as it approaches negative infinity, it does the same thing. However, the value is 1 here. Okay, now this is a little bit different from the last one. Well, this one, you can see that it keeps going. It's almost a linear, but it's still oscillating, but it's oscillating diagonally up into infinity. So as it approaches infinity, that also approaches infinity. However, this one, so here, this looks like a cosine or sine graph, however much the graph is shifted, doesn't really matter. But it follows that sinusoidal, that's what it's called, sinusoidal. And then it keeps oscillating. However, it keeps oscillating between the same values. Therefore, there's not actually a clear defined limit, or there's no clear defined value that it oscillates closer and closer to. So you would say that the limit does not exist. So this is a rule. So whenever there is any sort of constant, right, oscillation, you're supposed to say that lim f of x does not exist because oscillating. So actually, here we should write D and E because oscillating. Okay, so that's our lesson, that's the lesson over on limits graphically and numerically. This is our introduction to limits or calculus, but more specifically our introduction to limits. Our next video, we're going to be looking into solving limits algebraically. We sort of did it with our numerically, but that was a very broad introduction. We're going to go a lot more specific, learn different methods. So yeah, that's it for today's video. If you have any questions, leave them down in the comments below, or any feedback you might have. You can email me at dechoi101@gmail.com. And all right, that's it. See you guys next time.